My name is Peter Ebert. I'm editor-in-chief of inVision magazine, and I'm your host today. And before we start, I have a short question to the audience. If you hear embedded vision, what is the first name, what is the first thing that you have in mind? Is it camera, is it MIPI, is it deep learning? What is it? I'm a little bit of interested what you have in mind about this topic. Please use the Q&A or the chat function so I can see what your topics are thinking about embedded vision. So, and now we will start with our first presentation. It's from Sensor to Image, a Euresys company, and it is Matthias Schaffland who will make this presentation. So Matthias, maybe you can start with your presentation. And Heiko, Thorsten, maybe you can close your cameras.
Do you already see my screen?
Not yet.
Not yet. Ah, share. Now.
No, it's starting. It's not the presenter mode at the moment.
Now.
Yes, now it's perfect. Okay, you can start, Matthias.
Okay, hello everyone from my side. The first presentation from my side, from Sensor to Image. I'm talking about FPGA IP Cores as a building block to make embedded vision systems and how that helps to speed up your designs and get fast time to market. 2 sentences about Sensor to Image. We are in the market since 1989, a specialist for machine vision cameras. We started later in 2008 with FPGA IP Cores as standard products, and now we are we are proud to be the leading provider for FPGA IP Cores for these established protocols like GigE Vision, USB Vision, CoaXPress, and are serving a lot of customers with these IP cores. And since 2017, we are part of the Euresys group, what at the end brings a lot of strengthens our knowledge and market reach. What I want to talk about is first a typical architecture of an FPGA-based vision systems and what elements we can provide you to speed up that design here. So transport layer IP cores, sensor IP cores, and even if we don't offer that directly, I want to mention some aspects of image processing with IP cores to get the full picture. Then I give you a short overview about the typical design flow with this sensor to image IP core, so that you get an impression how that works. And finally, consideration about the time to market aspects, to get some information and to get some feeling why IP cores should help you to design your devices. Okay. Let's start with a typical design or typical architecture of a camera system, vision camera. So, of course, you have an image sensor from various manufacturers, and you want to read these data into your system, FPGA, SoC, something else. In that sense, it's agnostic to that. So you have a sensor interface in the first step to read out the sensors, to control the sensor, and typically you have some image processing block to make some pixel processing, and at the end, depending on the application, you output the data. And we are talking here about standard IP cores, so typically interfaces like CoaXPress, GigE Vision, USB Vision, or maybe others. On top of that, we have a camera control instance, could be a CPU or something like that, to control all these blocks here and to make things easier. The counterpart could be an embedded processor. Here you connect a camera system to a processing platform, again, FPGA, SoC, or something else. Here we have, again, camera interface to implement the transport layer, like again CoaXPress, GigE Vision, USB Vision, or something else, to decode the data. Then you typically do the image processing of the data in your device and communicate based on the results or whatever with external machines. For controlling the camera, you typically have again a piece of a block for remote control of the camera and processing control to configure and control these blocks for the streaming. What blocks do we now could help you? For transport layer cores, we can serve you with a GigE Vision IP cores for both cameras and receivers. This is widely available for 1G, for 10G, and we are working for 25 and even more G in the moment. All highly related to the GigE Vision standard. Very similar for the USB 3 Vision protocol. Here we have cameras and possibly receivers. Currently, we support only camera cores at sensor to image. Receivers is a bit more complicated and not so common. For CoaXPress, we again have both implementations for FPGAs, cameras, and receivers. So you can design or speed up your designs for cameras and also for receivers. That might be an embedded receiver or frame grabbers, stuff like that. This is both possible with this IP core. But I also want to mention other IP cores. Camera Link HS, for example, is maybe known. This is nothing what we offer, but from third parties, this is available. Sensor interface cores. Here we support the sub-LVDS protocol used in Sony IMX sensors. So if you use a sensor out of that family, you can use that IP core and quite easy and quickly connect your FPGA to that sensor. Newer sensors out of that famous IMX family use typically or often SLVS-EC for higher speed and lower pin count. This is offered by third parties. Also in the machine vision industry and others, the MIPI interface gets more and more common, and even for FPGA applications. For that reason, we have a MIPI receiver core for MIPI CSI sensors and some special sensors out of the IMX family or others. This is also available at sensor to image. For image processing, we have no direct offering, but FPGA vendors often offer suites like video suites or IP cores for image pre-processing. That could be scalar, color transformations, filter, stuff like that. So this is typically part of your, with or without additional license, part of your development license for the FPGA programming tool. Some FPGA vendors offer an additional tools like high-level synthesis tools to write FPGA code in high-level C or even C++ language. That makes it much easier to write your own image processing functions in not this deep VHDL or so language, but in a higher level language. These tools often include already image processing libraries, so you do not have to program all on your own. You can reuse existing libraries and extend that with your own functionality. And the output of such a tool is typically, again, an IP core, what you can use within the design tools for the FPGA. How does that look like with a typical reference design, what we deliver to you? So on the right side, you see the typical architecture, and here in the middle, a bit more text. So if we go through, on the left side, we have this image sensor where we could help with an IP core to decode the sub-LVDS protocol or the MIPI protocol. Then inside the FPGA, dependent if we have an external sensor or not, might be a test pattern generator without sensor, or if we have a sensor, then the sensor IP. Then there might be a frame buffer to store this information somewhere in external memory. And finally, we have a transport layer IP that implements the protocol like GigE USB 3 Vision, CoaXPress, to transfer the data over the medium and connect to the other end, so to the host side. As control unit, we use a CPU system that could be a microblade system, a NIOS system, or ARM system, depending on the FPGA, that also incorporates peripheral controllers like I2C or SPI or memory controller. And on that CPU system, we run some software with a lower level library. This lower level library typically implements the part of the transport layer protocol and the control channel typically of the control protocol, and of course the device application, which implements all your user specific registers and so on. So it's highly adaptable to your needs, and you can modify that simply in C source code. On an embedded processor reference design, this is quite similar. We have, again, our external camera, which is connected through, for example, CoaXPress or GigE with your processing FPGA. And the first block would be a transport layer IP for these protocols. And this block decodes the streaming and gives you the video stream. Based on that video stream, you can implement your image processing algorithm and all what you want to do. In our reference design, typically we have a video display and just display the image on a monitor to demonstrate how you can work with a decoded image stream. We again have a CPU system, which might run even under Linux to have more possibilities. And this is similar like in the camera use case. And here we also implement the camera control. So to connect to the external camera is typically initiated by the CPU system, and also the configuration of the camera, for example, setting exposure time, stuff like that. This is not done in VHDL stuff. This is done in C software or something like that, and could be easily extended. What is the typical design flow if you go with sensor to image and that IP? We have an initial phase guided by us. Here we try to find a common development platform with an FPGA as close as possible to your final hardware architecture. Typically, we use FPGA vendor evaluation boards. Here we have different possible solutions, or if this is all not suitable, we even have our own ones. It's the sensor to image machine vision development kit. Here we have, this is specially tailored for machine vision applications. Based on that development platform, we deliver a full working reference design, including all necessary interface cards. For example, to realize CXP, we extend that functionality by an FMC card. FMC is a standard for connector standard, and that helps us to extend the functionality. This is really a fully working reference design, not only an IP core with some more or less useful test bench. It's a full working design, so you can generate image data, you can connect it to your PC and to your frame grabber and see image data flowing. And this is then the basis is typically the basis for your own design. We also make an initial training on that reference design where we explain that in detail and the design flow, what to change to get a new feature at the end visible on your Genicam browser or whatever you have on your other side. So this is the essential part of our delivery. In the next phase, then that's your phase. You have to port the reference design to your final hardware. Of course, we help you with that. And then integrate your special sensor control and readout logic. Could be an additional IP or not. And you integrate your product-specific image processing functions, pixel operations, laser line extractions, white balancing, what is needed to make a good image and to be better than your competition. This is then your job here. On a processing board, typical remaining tasks are to integrate the camera control. Each camera is a bit different, and you might emphasize on different functionality. This is done in that. And of course, again, the application-specific image processing functions. Let's have finally some consideration about the time to market. To give you some idea, if you develop a basic division transport layer IP, you have to think about at least 6 months of work with to do that, and with ongoing maintenance work. So we started in 2008 with that, and we constantly have one person doing that and maintaining that and evolving that. So this is a never-ending story, I would say. But if you write GigE on your camera, there's no difference to another one to the camera. So it's really the question if that makes sense to develop that in your house. If you port the reference design to your production hardware, this is more in the range of 1 to 2 weeks in comparison. Similar with sensor integration, for example, SLVSEC, with an IP core, you can count with 1 or 2 weeks to integrate that and to get at least the basic image stream and communication to the sensor. If you do it from scratch, you again have to count with several months of work until you understand fully the sensor, how that works, and the protocol, and so on. So this is not so easy anymore, like maybe in former times where we have a simple parallel protocol. Finally, integration, pixel pipeline, image processing. Yeah, this is highly dependent on your requirements, but typically this is the main differentiation criteria to other products. So this is maybe the point where you should invest your time, because here you can specify what your camera or your processing system can do. The transport layer or sensor readout, this is just work. This has to be done, but you won't change the GigE protocol, for example, and you won't change the features of the sensor. This is given by the product itself. So doing pixel pipeline, image processing, this is where you should invest your time. So to conclude that, you have to count at least with a year of work, with that 1 or 2 persons full-time working to get a full working system. With IP, you have the chance to reduce that to an initial development time to 1 to 3 months. So significantly. Of course, this is only now the firmware. Hardware is a different story, and yeah, there might be ready-to-use hardware components as well. But from the firmware point of view, you can take that at least as some numbers for your decisions. Okay, that's all in the moment. Do we already have some questions?
Yes, there's already one. And the first question is, what FPGAs do you support with your IP?
We are quite flexible with the FPGAs. Mainly we support Xilinx and Intel FPGAs. This is the highest demand on the market, but we are constantly watching the market and see what is going on there. And yeah, we recently started to support even PolarFire FPGAs for lower end market share.
You mentioned some interfaces, and you mentioned also MIPI. Are you also looking at the new MIPI version 4, which will be more focused on image processing in the future?
Not yet, I would say, not yet. But here again, we check what is going on. FPGAs and MIPI is not the best fit, I would say. So it took a quite long time until the FPGA manufacturers saw the need to support them. So this is a bit behind I would say, the NVIDIA and whatever market, but they are catching up. But the newer standards here will go on as well. So in midterm, yes.
So looking at the clock, Matthias, I think we have time for more questions after our last presentation. So thanks a lot. So we're starting with the final Q&A session. So if you have any questions to the speakers, would be great if you just write the name of the company, so I know who should answer this question. And the first question is for, I have to see. Oh, it's for Matthias. What support services do you offer for your IP?
I mentioned that slightly a bit in the presentation. Key point is the full working reference design. You have seen this is a complex design. We have several IP cores, we have CPU, we have software, we have HDL, and this reference design helps a lot to get a quick start. And based on that, we have this initial training, and then we have a certain support budget within the license over a certain period of time to help you doing your hardware, review hardware, and then also to help you porting the IP to your hardware.
Thanks. Now I have another question. It's first for Matthias, but maybe also for Thorsten and Heiko. You mentioned different interfaces at your speech. For example, there's Camera Link HS, and so now companies like Ximera and Matrix Vision started with PCI Express cameras. Do you think this is also something for you in the near future, or will be also a topic for Lucid and IDS?
On our side, at least not in the near future. Of course, we are part of the standardization committee, like Lucid and IDS as well, and we are checking and discussing that with other companies. In the moment, we see not too much benefit, short cables and so on. We are more on this CoaXPress or 10G or 100G path for that, but say never know. We watch that and see what is going on here in the future.